Today I'm willing to move on to the application part of the GARCH nonlinearity invariance chapter. The application part will be quite complicated and maybe we'll not be able to cover it in 1 or 2 videos, but we'll try our best. We have completed the chapter and basically I believe we are almost at the end of our discussion for postgraduate research related econometrics discussion. So to begin with, we will look into our problems that we want to discuss. We have already slightly discussed some of the problems in earlier video, and we have covered up until GARCH mean. So now we are gonna move into we're gonna start discussion from there. Now in the last video we have talked about GARCH M, ARCH and NH, and also we talked about how we can model risk in term structure of interest rate, where the parameter phi captures the risk neutrality. Today we're gonna start with GARCH model with conditional student T distribution. So let's have a look into problem number 8. Now this data is based on the same data we have used before. We're gonna follow this GARCH 1.1 model, and we have to understand why we are doing this problem, but we'll look into the theory part very quickly. Now here, y is the percentage return on FTSE. Compare the GARCH point estimate with those presented in some table which are based on conditional normality. Interpret the estimate of degrees of freedom parameters tau. So we have to estimate tau now this time and discuss its implication for the existence of moments of the conditional distribution of y. And then we are gonna talk about a bit of asymptoticity. A limiting case of student's distribution occurs when the degrees of freedom approaches infinity. We need to construct a word test of normality under now when the inverse of tau equals 0. We need to re-estimate the model assuming a constant conditional variance by imposing the restrictions which are alpha 1 equals beta 1 equals 0. We want to compare the estimate of degrees of freedom parameters that we have obtained here, and hence discuss the effects of GARCH conditional variance on modeling the distribution of y. So this problem is revolved around the distribution of GARCH, and why this is important, or student's distribution is important, because we need to understand that when we are trying to draw GARCH or specify a GARCH model from normal distribution, then we will not be able to capture all the elliptokurtosis in the data or the volatility in the data basically. So we combine conditional normality with GARCH variances, and there are common approaches starting with the parametric approach, and the parametric approach is to replacing the conditional normality specification. So the conditional normality specification will be replaced with a T distribution or another parametric distribution, which is another parametric distribution that exhibits kurtosis. So basically conditional normality specification or distribution will be, the normality distribution will be replaced, so a regular distribution will be replaced with student's T distribution, and then combined with GARCH we should be able to capture better leptokurtosis or the volatility in the data. So when this is the basic GARCH model, the conditional distribution of Z is chosen as the standardized student T distribution. Here Z is mu equals sigma Z, or Z equals mu divided by sigma, something we need to remember. Tau is the degrees of freedom with the mean 0, variance 1, and what is the T distribution is the gamma distribution, which is quite simple. starting for z is gamma tau plus 1 divided by 2, so we need to remember the part which is tau plus 1 divided by 2. So the first element is gamma tau plus 1 divided by 2 divided by root over pi gamma pi tau gamma tau by 2. So gamma is there in numerator and denominator both, and that is multiplied with 1 plus e square by tau, where e will be replaced with z to the power gamma plus tau plus 1 divided by 2, which is the degrees of freedom portion. Now e itself has mean 0 and variance tau divided by tau minus 2. Now when we define the standardized normal variable z, the standardized normal variable z is simply e divided by root over tau divided by tau minus 2. This is something we need to memorize, and then using this information we transform from e to z, where we have absolute value of root over tau divided by tau minus 2, that element from here e by v, because we're talking about this equation dE divided by dz, and the EE crosses out, so we're left with where EE, when EE crosses out, we are left with root over tau divided by tau minus 2. And if it is simply z, mu equals ut sigma z, mu equals sigma z, where we replace that with z root over tau divided by tau minus 2. And then we have the t distribution, and from fe to fz, the only change is the numerator and the denominator with the gamma portion remains same. Root over pi tau becomes root over pi tau minus 2, that's all. And this portion changes, e square by tau becomes z square by tau minus 2, so all the taus become tau minus 2 and the rest remains same. And then we have the log likelihood function representation, where the log likelihood function starts with half log square plus log over log of the function of z, and simply when we log it, the function of z, this element comes forward, that's all, nothing else. Is quite simple. And we have several theta parameters. Obviously we have alpha, not alpha 1 beta 1, but we have tau. We enforce, make sure that tau doesn't gets less than 2, otherwise we have zeros. Now when we move to GARCH parameters, focus on GARCH parameters. Obviously log likelihood function, we first difference gives us the gradient, then in the gradient we also have, we can find a variance covariance matrix from there, variance matrix, the variance, and also we can find the covariance matrix from squared gradient, and also the Jacobian J, which is simply the inverse of theta. So using this and the question which is, and the question gives us the same problem, we will leave ourselves to page 28, and we need to page 24, and we need to remember that for this problem this time we're not gonna, for these problems we're not gonna open R, we're gonna look into MATLAB, because well, it's gonna take a considerable amount of time going through these exercises, and they're quite difficult. So there is probably no point right now to look into R conversion. You'll probably be able to find how to convert to R, or maybe later we can focus on it if we if we have enough energy left, or maybe never. So it's better to look into one application for difficult problems for now. So how do we do the students' redistribution problem? Let's see. So first of all, we need to look for local functions. Obviously there is log likelihood function, and we know we need to create one wrapper function every time which is log of beta. B is theta, where all the theta parameters always come to b, and y, which is minus mean of log LTBY. So that has been set, and then the main function. Okay, so the GARCH model. First we start with the GARCH model. Then first is unrestricted, then restricted. So log LT by, and b is all thetas will be in absolute value. We expect all thetas to be in absolute value. T is obviously in the number of observations we have. U is equal to y minus, well, y minus beta 1. This is a bit of change from the regular thing we have learned up until now. We are saying that error is y minus beta 1, and obviously I think our beta 1 is alpha. In this problem, our beta 1 would be is theta 1, which is alpha 1. So okay, so there is the question. All right, and we don't think our beta 1 is alpha 1. No, I think our beta 1 is gamma naught. So y minus, so that is the part. We have u equals y minus beta 1, which is gamma naught. Okay, fine. And h is equal to standard deviation of, h is simply standard deviation of y square, which is first to store data, y square multiplied to once zeros. So the constant variance that we have, we want it as a vector, so we are converting it into a vector. Then obviously for 2 to t, that is how it goes. For d I equals 2 to t, our GARCH estimate is beta 2, which is alpha naught, then beta 3 ui minus 1 square, beta 4 hi minus 1. So the arch parameter coming from the residual, the arch parameter, and the GARCH parameter indeed. And then log LT, which is the log likelihood function, which is half log sigma square. Again, the half log sigma square is h itself. Then log of gamma. So beta 5 is our tau. So tau plus 1 by 2, something we can recall, or we can go back to our equation. Let's go back to, so this is our equation we have, and gamma beta 5 plus 1 by 2, then gamma beta 5 minus 2 to the power half, which is the root over, then gamma beta 5 by 2 minus beta 5 plus 1. Okay, so minus beta 5 plus 1 by 2, the log likelihood function becomes 1 plus z square. Now z we did not calculate before. Z is simply u by 2, because yeah, z is simply u divided by sigma, and that's not a matrix by matrix, it's an element by element estimation. So u divided by sigma, which is the standard deviation, square root of h squared divided by tau minus 2. Now that is your log likelihood function, quite simple. Then for the restricted model, our parameters will drop slightly. We have to repeat everything as it is. It's just h changes, where the variance is the variance is when alpha and beta are 0. Let's go to the question. You see, when so we are in page 49, when alpha and beta are 0, we are only left with alpha naught. So because we are comparing with this scenario, So we're just estimating beta 2, but we repeat everything again for the sake of our simplicity. So we load the data and we find the difference, the log difference, and we make a percentage of it. Then obviously we take a mean difference, y minus mean of y. So the percentage return and subtract the mean. So we have found the percentage return, we subtracted the mean, and because the question suggests us to do so, let's have a look one more time. Why not? The question asks us to find percentage return to the so this is what we always do with return data. Then we optimize. This is just a random initialization for gamma, alpha naught, alpha 1, beta naught, tau. Now you can begin with any numbers you want. I generally go for randomization or random with random stream, and that yields good results. There is no question about that. So when we run this function, we don't have to go for all those difficult questions because Hessian is estimated and variance and everything is estimated. So inverse of Hessian, which is mentioned in our problem, basically in page 24, inverse of Hessian gives us variance covariance matrix. There you go. Standard errors. Unconditional variance is theta 2 is alpha naught. So alpha naught divided by 1 minus alpha 1 minus beta 1. So constant divided by the coefficients portion. That is very common equation we have used several times before. Just try to visualize and remember, think that if we have replicated this before, we have done it several times. So constant alpha naught divided by the coefficients 1 minus alpha 1 minus beta 1. Very simple. And unconditional variance. Now we are to do an word test with a transformation. So C is equal to 1 divided by tau, theta 5 is tau, Q is 0, and Jacobian is minus 1 by tau square. Jacobian is minus 1 by, theta 5 is tau for sure, because theta 5 is tau, and tau square maybe is coming, it has something to do with this part, right? GG theta, because in G did we have tau square? Oh yeah, we had, no, we didn't have tau square. So just some things we cannot learn without the application, so just remember it. Jacobian is it's a return data, so tau square, fine. And the word test is C minus Q inverse of DC, C minus Q. I got stuck here. Alright, I'm not sure why we are squaring tau. Maybe we'll be able to find the answer, not today. Well, there's a d sigma square theta. The estimated covariance is if it's tau, outer product gradient. Alright, just remember it. So this is how we do the word test, and this is the same thing, C minus Q inverse of DC, VC and DC. It's a bit different representation. The equation remains same, but C and DC and Q, these are different in different chapters, that's all. And again we do the restricted estimation. we estimate everything. Maybe the restricted estimation gives us unrestricted log likelihood, because that was what was asked in the question. So that was a simple students t-distribution example. Quite not simple, there are some confusing points, but yes, now we are expecting that there will be some confusions. Then another another quite interesting question is quasi maximum likelihood estimator, which is another form of putting in leptokurtosis in the parametric estimation when we have non-parametric estimation. So we are considering a GARCH 1-1 model. Again, y equals mu error is sigma z and 1 minus alpha 1 minus beta 1. Okay, so in place of alpha naught we are putting the rest that we have always talked about, a1 b1. The aim of this exercise is to investigate the efficiency of the quasi maximum likelihood estimator relative to the maximum likelihood estimator of the parameters. Here most important is the definition of quasi maximum likelihood estimator, and we will look into that. So we are going to let the true distribution of z be students t with tau naught degrees of freedom, meaning to write the log likelihood function for observation t and derive an expression for the covariance matrix of the MLE that I had of the true model. We want to let the variance be covariance of alpha hat and beta hat. We want to let the misspecification distribution of z, misspecified distribution of z to be in 0, 1. We'll talk about it. We want to write the log likelihood function for observations, so we can use students t distribution, and variances will be alpha 1 square and beta 1 square, right? And we're going to use the t distribution, and the distribution of z will be 0 mean 1 variance. Write the log likelihood function for observation t and derive an expression for the covariance matrix for. Okay, so this is with students t distribution, this is with gamma distribution, this is with quasi maximum likelihood distribution, and we want to simulate 100,000 times with given degrees of parameter. We want to find take the difference, the fraction of covariance that we have estimated with t distribution and quasi maximum likelihood distribution, and we want to compare those results, and we want to repeat them, changing the distribution when we have a gamma distribution with a shape parameter C50. So this is quite big and to some extent I believe a bit unnecessary, but we'll look into it as much as I can. But yeah, before that, the important discussion, which is non-parametric discussion. And what is non-parametric discussion? You see, dealing with we have tried to deal with leptokurtosis in volatility, capture leptokurtosis in volatility with distribution. However, in a normal distribution, if we do not account for leptokurtosis, the log likelihood function is misspecified, but we can still use the misspecified log likelihood function because it will still give us correct mean and variance. However, when we use the misspecified log likelihood function, it gives us quasi-maximum, it calls the quasi-maximum likelihood estimation or quasi-maximum likelihood function. So the theta that we get are the estimators of quasi-maximum likelihood, and the standard errors are given as the diagonal elements as always, Hessian, and everything remains same, right? Log likelihood function at a specified point is yty sigma square, always being the same, and gradient and Hessian is generally automatically estimated without optimization. We generally have 0 mean and 1 variance in quasi-maximum likelihood estimation. That's what it is mentioned here. And then we can move on to taking more derivatives it will still give us 0 mean and standard deviation, which means that for all higher order, quasi-maximum likelihood estimator is a consistent estimator of the true population parameter. Okay. Now, when we take a higher order differentiation in our gradients matrix, our mean is 1 and variance is 3 plus 6 by tau minus 4 using law of iterated expectation, which is t distribution. Basically, at a higher orders, our specified model gives us results similar to t distribution. Okay, so let's see how this is done. We are talking about two types of problems here. By 40, let's go to 50. Our problems are GARCH student and GARCH gamma. So have a look into GARCH student. It's gonna be a bit difficult in terms of programming, but we'll start with the functions. Obviously, I will wrapper function, then GARCH t1, v equals y given to us, then sigma square. Because we have to do it 100,000 times, we want a recursive or replication. So we'll put the whole thing in Rexarer function, the whole equation. So first comes the equation 1 minus beta 1 minus beta 2 plus beta 1 so plus beta 1, that is a constant amount, plus beta 1, right? Let's see what was the actual question. Oh gosh, so not this one. A1 v square minus 1. Okay, now comes the point of the function itself. Have a look into the function itself. Let's have a look into what Rexarer function looks like. MATLAB functions, Rexarer. Yeah, it's for recursive estimation. That's all that I can recall at this stage. Oh, thank God. So what are the inputs? X, Y naught, A. X, Y naught, A. That's all we need to remember. So X constant here. Y naught is beta 1. Taking beta 1, 1 minus beta 1 minus beta 2, okay, beta 1, and then we are stocking v square. So v is y, and we're taking the squared return as representing the variance. So first row is 0, then so 0, and then starts all the y squares. We trim nothing from that, we let the system have 0 and just we trim the last row so that dimensions match. X, Y naught, so this is the whole X thing. There is yet no Y naught. This is the whole X thing. 1 minus beta 1 minus beta 2 plus beta 1, right? So alpha 1, 1 minus alpha 1 minus beta 1, then plus alpha 1. Though in the question you see this is how things become difficult. Though in the question A1 is mentioned, there is no A1. A1 is alpha 1, and we are stocking information into alpha 1. Y naught. Y naught is just simple standard deviation of taking the standard deviation of y and then squaring it, initialization, and A is beta 2. Is another different parameter. Then nu is beta absolute value of beta 3 that we will be using, which we have been calling tau. I'm sorry. and z. So this is the log likelihood function. Let's make it a bit simple. Okay, so gamma nu plus 1 by 2 divided by square root of pi nu minus 1 by 2, or what we did before is pi nu minus 1 by 2 to the power 0.5 multiplied to gamma nu by 2. This is the regular thing, the regular element of the equation that we jack into the log likelihood function. Okay, of log nu plus 1 into log of 1 plus the square divided nu by 2, nu minus 2. This is the actual equation for t distribution. Still is good to have a look. If we are going to the parametric distribution and t distribution, yeah, nu minus 2. Fine, that is good enough. Then we move into, this is our GARCH T11 model. Then again the wrapper function, GARCH T model. Now this is quasi maximum likelihood function, and in quasi maximum likelihood function is student's t distribution, where the only thing is y by sigma square, which is square root of u divided by square root of a z square, basically z square. Okay, everything else remains same. This is a simple equation, half log sigma square, half log z square, right, for the quasi maximum likelihood function. Yeah, so if we have a look into the basic function, the basic log likelihood function, u square divided by sigma square is equal to z square, because y equals mu, and when y equals mu, you have mu by sigma square, which is your z square. There you go, y equals u divided by sigma square, z square. Alright, so you have defined the two equi functions. Let's run it 100,000 times. So I create a z with random numbers, u equals z, y equals z. I'm just stocking things in because it's a simulation problem, into u and y, and I'm creating storage for the standard deviations. A1 is 0.1, B1 is 0.8 given to me, or as assumed initialization, and I'm taking 3 news. I think these news are given to me in the question. Oh no, it's not given in the question, it's given inside the chapter. Yeah, when talking about efficiency comparison, I told you, you see 0.1, 0.8, alpha 1, beta 1 is given to me. A naught is calculated from alpha 1 and beta 1. Okay, fine. Which is 0.1 and tau 5. So given this information, I jack those in 5, 8, 11. Beta 1 is, I'm not sure how beta 1 is. Okay, 1 minus a1 minus beta 1 gives you 0.8. So 1 minus 0.1 minus beta 1, you solve for it, you should have 0.8. Oh, beta 1 is already given to me. Okay, new 5, 8. What I was thinking about, why do we have 3 news, right? So maybe they are just assumptions. Alright, fine with me. So T inverse is something that we haven't ever used before. It creates a T distribution for you based on given information. I've just asked MATLAB to open the help for T inverse. Let's see what T inverse means. Students, T inverse cumulative distribution function. where it takes in a distribution P and nu inverse of, and it gives the inverse of students T cumulative distribution function. Good, because it gives you an inverse of the T distribution function, taking a P and a nu value, and they should, values of P should locate within 0 and 1. And why are we taking the distribution, and we are trying to inverse T? Because that is what is expected of us. Let's have a look. So somewhere around here, this time we need to take a T inverse. We need to inverse the student's T distribution. Somewhere around here, I kind of missed it, I guess, but it's for sure. So randomize a number, T rows 3 columns, because I have 3 data. Maybe I have 3 sets of data. Then we create a ones matrix where diagonally I have the nus 5, 8 and 11 located, and I'm just inversing them. Then parameter values for the first model, so let's loop in 2's first across columns, then across rows. So 1 to length of nu, which is 3 columns. I need to generate data for, I want 2 to T, where Z is what student's T disturbance, nu minus 2 divided by nu multiplied to weight, W is weight, multiplied to the T inverse thing. Then this is the regular equation, this is the regular disturbance term, so this is where the tweak is, which is yeah, just a simple tweak. I'm just looking for anything that might get me hooked. This C 5, 8 and 12 is given to me, and yeah, okay, let's see. But did I jack in random T3, random T rows 3 columns is my probability distribution. Random is uniform randomization, so values located in 0 and 1, and once row P and nu, this is nu, so diagonally we have the new values of ones, T rows 3 columns, nu, so this is quite huge degrees of freedom. We fix our Z accordingly. This is the tweaking part. Efficiency based on analytical derivatives. Okay, so recursive, run it recursively for stock into column 0, then y square, last just take the squared return, fix the last one minus 1 so that everything below locates within 0 and 1. then 0, then B1, H01, H and Y, that's all. DS2A, DS2B, DS2E is both of them. Covariance of H, inverse of something, beta 2 given to us. Covariance of J, inverse of beta 2, minus 1 to something, I'm not sure. Covariance of quasi maximum likelihood estimator. Covariance of Jacobian, okay, beta 2 minus 1. I'm not sure how I'm getting 0.25. It's a bit tiring. Somewhere from here, 0.25. Okay, now it makes sense. 1 by 4. All right, fine. 0.25, 1 by 4. So covariance of J is the whole thing being inversed. Beta 2 minus 1. Mismatches of the true model. Let's skip this part. This is somehow no, gradient. Okay, covariance of maximum likelihood estimator, numeric gradient. Times 61 is multiplying DS2 with this, which is nu plus 1 divided by y square, sigma square, divided by sigma square plus h nu minus 2 something, not sure what it is. It must be, I must be lost somewhere around here in the big equations. So I do not think I'll be using them, so I'm just gonna keep them as they are and move on. And then okay, so that was it. Let's see how the gamma distribution looks. We understand up until how functions are created. They're not difficult. We understand how the gamma function is created, and everything else is just a repetition of the previous solution. TMP D1. Okay, this is gamma distribution. That's all. Gamma elements C minus Z square. So just have to look into the equation to understand how this goes. And then the number is also created in gamma. So let's skip this. We don't want to proceed with that. This is really a difficult problem because it will take, it's not a difficult problem, it's just replication from everything that is in the book. Very less practical, will be less used because I'm not gonna compare between two distributions probably. So let's move into a very important problem, as I feel, a mixed data sampling estimator. Come back. Mixed data sampling estimator, or MIDAS, GARCH MIDAS. This is an important question because we're going to talk about realized volatility. Here the data are 2,179 daily prices on the convertible arbitrage hedge fund index and the S&P 500 index from March 2003 to August 2011. As an alternative to the RSM model, MIDAS estimator has been proposed. What is the benefit of MIDAS estimator? The benefit of MIDAS estimator is that it is a mixed data sampling estimator. which means your data might not have the same features. It might be different, but it is convertible. Here the monthly conditional variance is computed as a realized volatility, which is being weighted average of lagged squared daily returns. So the monthly conditional variances represent realized volatility, but those realized volatility are weighted average of lagged squared daily returns. So daily returns are squared and they are lagged. So you have the model where R is the monthly return on the hedge fund that I'm trying to estimate. M is the monthly return on the market. Okay, so not trying to estimate. Hedge fund is given to us, M is given to us, we just need to find the coefficients. Sigma square is Midas conditional variance computed from lagged daily returns, and D is the dummy which captures global financial crisis, which equals 1 on the day of biggest fall in the monthly returns are and 0 otherwise. So when the monthly returns are the minimum, that becomes 1. Okay, fine, makes sense. So lagged daily returns are weighted and then averaged. So sigma square is basically I equals 0 to NL. NL captures N is the number of days, lagged square daily returns, number of days, and they are then lagged. So number of days is in 2012. L is the lag length in months. Okay, that we want to estimate probably. Yeah, and 22 days in a month. Then R square minus 1 is the lag minus I. 1 minus I, okay, fine, is the whole lag thing multiplied to comma is lagged squared daily return, lagged squared daily return. The weight is exponential of 1I plus alpha 2I square divided by summation I is equal to lagged n monthly 22 days exponential alpha 1I plus alpha 2I square, so exponential distribution. So we want to compute monthly returns are from daily returns are, so we are computing monthly returns from daily returns assuming there are 22 days in a month. First conversion. Then we want to estimate all these parameters: beta naught, beta 1, beta 2, beta 3, alpha 1, alpha 2, where maximum likelihood and Midas variance based on the lag length of L 18 months. So L is 18 months given to us lag. Then there's a restriction with setting alphas to be 0. In the intertemporal capital asset KPM model, the parameter beta 2 represents, so when you're talking about a KPM model, the beta 2 represents coefficient of relative risk aversion. Coefficient of relative risk aversion. Interpret the parameter estimate obtained in part B. Okay, fine. Beta 2 represents, for a hedge fund to be market neutral, the restriction is beta 1 equals 0. M is monthly return on the market, and if the hedge fund to be market neutral, then this term turns to 0. Conditional variance is here, and beta 2 captures risk neutrality or risk aversion. Compare the result. Test the restriction using the result in part B and compare this result. When we set beta 2 equals 0, that means people are risk neutral. Briefly discuss the potential problems. and define lag lengths. So this is your Midas problem, right? Let's see how Midas problem works. First, let's have a look into functions. So quite large function. First of all the thetas, then RH, RM, RHD2, D, GFC. Let's see what RH is. RHD itself is daily returns on the hedge fund and on the market. RHD is return on hedge funds on a daily basis, simple log difference, daily returns on market, then convert to monthly. And this is the tricky part, we are doing it for the first time ever. You use the reshaping. What is reshaping? Let's have a look into what reshaping is. It simply reshapes the dimension, but let's have a look. So first we take Y, and Y is converted to the number of rows and columns we want. So our return on the hedge fund on a daily basis is our Y, and we want rows. How many rows do you want? The total number of daily hedge funds divided by 22, because we are cutting each month down to 22 days. Great. So divided by 22, that many rows and columns will be 22, because now each rows is trimmed down and we have each day's conversion, so 22 days. So the data contains 22 days hedge funds daily returns. Okay, and summation is, this is dimension, the second dimension, okay, which means sum them up by columns. You need to be sure. Let's have a look. So sum all the columns up. First you convert 30 days to 22 days, data is set to 22 days, and think about what you have in the block of data. By rows you have that after divided by 22 that many days, and by columns you stock each day's, by columns each day's hedge funds returns. Then you add them up fully. Sum dimension is by column, and then you add them up, then you have monthly returns, RH, and for market also. We have lag 18 given to us. TM is length of RH, we know number of months in the monthly dataset. TD, number of days in the daily dataset. TD by TM, number of days in a month, in rounded. This is interesting as well, how we can convert it, number of days to number of months when we don't have actual number of days or months. And already lagged given, so 22 RHD square is in the question already. 22 and RHD is hedge funds daily returns squared, right? Hedge funds daily returns squared. You have everything else, and we want to construct the dummy variable for global financial crisis. So month, let's look into months. As many months we have, we put them to 1, because we are trimming the whole thing down to months, so dimension should be months. And in K we want only the minimums, because in the question it suggests biggest fall on monthly returns. So biggest falls are located in the minimums, we put them 1. Great, data is set. let's have a look into log likelihood function. So monthly on hedge fund, monthly on market return, daily on hedge fund, RSD2. Oh, okay. So this one, sigma square, directly from the system. Financial crisis, we don't have any information on this. We want this to do all the estimations for us. TM, N, lag, good. Maximum likelihood function is awesome. Theta 1 is a magic. Theta 1 is B5, theta 2 is B6, right? And theta 1 is alpha 1 and alpha 2. We are talking about alpha 1 and alpha 2. And let's pre-compute weights first. N into lag, maximum lag is NL. N is 22 days and lag is 18. Then we want a get weights function. So what was get weights function? Theta 1, theta 2 max lag. So theta 1, theta 2 max lag. Okay, fine. Maximum lag, this will be estimated. So I equals 0 to whatever maximum lag is minus 1. Maximum lag is 18 minus 1 by 1s. Then W is equal to exponential of theta I divided by, also just simply that, exponential of theta I divided by 1.0e2 plus theta 2I squared divided by something. Okay. Oh, so exponential portion is being calculated. Theta I divided by 1.0 E2, I'm not sure, 1.0 E4, what is 1.0 E2, 1.0 E4 squared. Okay, fine, divided by. So we have these thetas, and W divided by sum of W gives us get weights. So we call for the get weights inside this function. We call for another function. Variance, monthly variance is 0, TM1. If max lag is greater than number of days in a month, then pad the returns. So maximum lag is not greater than number of days, it's 18 days and it's 22 days. If it is greater, then in our hedge fund daily return, we want zeros of max lag minus n, which is 18 minus 22. So whatever, if suppose it has 24 lag and 22 days, so 2 rows 1 column, there will be 2 zeros, then it will start. So we're gonna stock into column as many number of lags exceed number of days, we have as many zeros to start with. So k is equal to 1. For j is equal to max lag, we have always been, subtracting. So plus 1 to length of RHD plus 1, increasing by 1. So from max lag to the length, so if max lag is 22, 23, if length is 2000, that many columns, basically this is column. For I is equal to 1 to max lag, calculate this VMK plus VMK, RHD2 j minus 1, wait, okay, plus minus I, j minus I, wait, okay, RHD2 squared. Adding to the monthly thing, KK plus 1, and trim extraneous startup months and lag the results. So whatever extraneous was, if it was greater than 1, we would trim it. So then we have V, which is simply the equation we talked about, and this and this. So basically this is how it is. Midas model, where we get realized volatility. And what is the realized volatility? When we have weighted average of lagged square daily returns. When we have weighted average, so your returns are basically weighted, and that's realized volatility. The beauty of this system is it can capture only the effect of financial crisis periods when you have realized volatility. There's a lot of tweaks in this problem, lot of complications in this problem, quite a difficult problem, I must say, because a lot of trimming and a lot of adjustments to the dimensions, and I'm not quite sure how this has been done. See, if we have 3 counters, why do we need 3 counters? Kij to compute Midas variance. K is a simple placeholder for the calculated monthly variances. I loops over the daily data and is incremented by the number of days in month. Okay, 1 to maximum number of lag goes up by 1. J loops from 1 to max lag over the daily data to compute the required summation. J is starting from max lag to the last, incremented by the rounded number n. So in a monthly way it rotates, I mean the speed, it rolls over on a monthly basis. And what is VM? Variance of the market. And the variance of the market is whatever you calculate, because it's kind of, though it's a for loop, it looks like a while loop, added to the squared returned the realized volatility. This is the monthly volatility, which is the realized volatility. So counter k, it will go on for k plus 1, otherwise the counter will not execute, that it ends here. So it starts at k. It's another example of how you can use for loop in place of while loop. It looks like it's a while loop, but you can do it with for loop too. Wow, very good programming. If somehow max lag was greater than 1, so the first part is, if ever number of lags is greater than number of days in months, whatever the number of lags by which is it exceeds the number of months, you put all of them to be zeros. For example, if we had 26 lags and 22 dates, 4 zeros to start with, then comes the realized volatility part. No, the returns, squared returns. This is the input data that we are using, and then we found realized volatility, and then comes trimming. And as long as lag is greater than 1, we trim our realized volatility, lag -1 rows. I mean the first lag -1 is trimmed as it greater than 1, a lag -1 is trimmed, and from last one is trimmed. So whatever the lag was first, from that one is trimmed, from last one is trimmed. If lag is greater than 1, else we just trim the last one. Obviously lag will be greater than 1. Lag is 22, so first we trim 22 from the lag. By this amount we trim the rows, and just 1 from the columns. If lag was never greater than anything, 0. Okay, this was not necessary, because obviously if lag is 0, then nothing is getting trimmed. And then finally we have the variance, which is we took the we took what? H. We took is RH. R is hedge fund on a monthly data. Yeah, we took RH and we trimmed the lagged amount. We don't need the lagged amount. Nothing from last. Then RH minus V1 minus B2. Okay, this is the equation part. This is residual from the equation. And what was the equation? This, everything else goes to left hand side. Minus beta 1 minus beta 2 trim RM. Again, monthly lag amount is trimmed. Lagged amount has always been trimmed. Good. V3 VTMP. We are not doing any trimming here because we have done the amount of trimming with an automatic coding here. Good. Then financial crisis, and then sigma square variance, Z, log likelihood function. Beautiful. It's a beautiful problem. So that was Midas, and this is how Midas weights are distributed. It says they are distributed normally, which is real good information. World statistics, optimization, finite difference. Can we remove these just for a second and see how this looks? Can we get some outputs? Yeah, we got the outputs. See, we have RHD to RM or V. What I'm looking for is V. Wow, we have 99 financial crisis captured. 99 monthly returns, daily returns, total monthly returns, variance covariance matrix. So we never wanted to find, V. The value of V is our realized volatility. Have we found V? For some reason, okay, that is within the log likelihood function. Oh, I missed that part. So we optimize. After optimization, 1 divided by 10 minus lag multiplied to inverse of Hessian, and we plot the Midas weights and we do our test. That's all. So when theta 5, theta 6, alpha 1, alpha 2 equals 0. So when we optimize, we get we don't get V here. V is none of our concern. We want the theta parameters. We get everything actually, RH, RM, everything that we want. RH, RM, beautiful. RG2, DGF, CTM and lag, everything that we need, and all the theta parameters in V. Okay, I'm sorry. Let's have a look into B. Okay, so that's what we needed to know. Return on monthly, variance covariance, the weights, everything. Pretty good. So we don't want to save it. We want to keep the results as it is. So it helps us to find realized volatility, which I believe was awesome thing to learn. And so we don't know. So we're gonna come back with more multivariate GARCH.